Tonight, we are going to explore something you interact with every single second of your life, but have probably never truly understood. The electron. You have heard of it? You know it is part of an atom. But here is what almost nobody realizes. The electron is not a tiny ball. It is not a little sphere orbiting a nucleus like a planet orbits a star. It is something far stranger. And once you understand what an electron actually is, you're going to realize something that will change how you see the physical world forever. You have never touched anything. Not once. Not ever. Nothing in the universe has ever touched anything else. And the reason why is one of the most beautiful and mind-bending revelations in all of science. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. Let us start with something that seems obvious. Matter. The stuff everything is made of. You, the device you are listening to this on, the chair you are sitting in, the air you are breathing, all of it is matter. And for most of human history, we had no real understanding of what matter actually was. We could see it, hold it, shape it. We could tell the difference between wood and stone, between water and sand. But what matter was made of at the deepest level remained a complete mystery for thousands of years. Ancient Greek philosophers debated this endlessly. Some believed everything was composed of 4 fundamental elements: earth, water, air, and fire. Mix them in the right proportions and you could explain any substance. It was elegant in its simplicity, but it was wrong. Others, like the philosopher Democritus around 460 BCE, proposed something radically different. He suggested that if you kept cutting a piece of matter in half, over and over and over, you would eventually reach a piece so small it could not be divided any further. He called these fundamental pieces atomos, which means uncuttable. It was a brilliant intuition, an idea so far ahead of its time that it would take more than 2,000 years for science to catch up. And when science finally did catch up, what it found was both a confirmation and a shattering of that ancient idea. Atoms exist, but they are not uncuttable. They have structure. They have parts. And those parts behave in ways that defy everything we thought we understood about reality. By the 1800s, chemistry had firmly established that matter is made of atoms. Different elements have different types of atoms. Hydrogen has one kind, oxygen has another, gold has another, carbon, iron, nitrogen. Each element corresponds to a distinct type of atom with specific properties. The periodic table, first organized by Dmitry Mendeleev in 1869, arranged these elements by their properties and revealed repeating patterns that strongly hinted at some deeper, underlying structure. But even Mendeleev, brilliant as he was, had no idea what that structure might be. Atoms were still imagined as tiny solid spheres, indivisible, fundamental, the smallest possible units of matter, the uncuttable pieces that Democritus had imagined 23 centuries earlier. That idea held firmly in place until 1897, when a British physicist named Joseph John Thomson performed an experiment that shattered it forever. Thomson was working with cathode rays. These were mysterious beams that appeared inside sealed glass tubes when a high voltage was applied across metal plates at either end. When the voltage was switched on, something streamed from the negative plate, the cathode, toward the positive plate. This stream could cast shadows, suggesting it traveled in straight lines. It could be deflected by magnets, suggesting it carried electric charge. Scientists had been experimenting with cathode rays for decades by this point, but nobody knew exactly what they were. Some physicists believed they were a form of electromagnetic radiation, like light. Others believed they were streams of charged particles. The debate was fierce and unresolved. Thomson designed an elegant experiment to settle the question. He built a carefully constructed cathode ray tube and subjected the beam to both electric and magnetic fields, carefully controlling each one. By measuring exactly how much the beam bent in response to these fields, he could calculate the ratio of the electric charge to the mass of whatever was carrying the current. If cathode rays were waves, they should not be deflected by electric fields, but they were. They bent, decisively. This proved they were particles, not waves, but the truly shocking result was the charge-to-mass ratio Thomson calculated. The particles in cathode rays had a mass far, far smaller than the smallest known atom, hydrogen, roughly 1,800 times smaller. This was revolutionary. If these particles were smaller than atoms, then atoms could not be the smallest things. Something existed inside atoms. Something even tinier. Something more fundamental. Thomson had discovered the electron. He initially called them corpuscles, but the name electron, which had been coined a few years earlier by the Irish physicist George Johnstone Stoney to describe the fundamental unit of electric charge, eventually became standard. Thomson's discovery earned him the Nobel Prize in Physics in 1906, and it opened a door that could never be closed. Atoms have internal structure, they are made of smaller components. The uncuttable was, in fact, very much cuttable. Thomson proposed the first model of atomic structure, which came to be known as the plum pudding model. He imagined the atom as a uniform sphere of positive electric charge, like a pudding, with negatively charged electrons embedded throughout it, like plums or raisins scattered through the dessert. The positive charge and the negative electrons balanced each other, making the atom electrically neutral overall. It was a reasonable first guess. It explained why atoms were normally neutral and why electrons could be knocked out of them, but it was wrong. The plum pudding model was demolished in 1911 by Ernest Rutherford and his colleagues Hans Geiger and Ernest Marsden at the University of Manchester. They performed what is now one of the most famous experiments in the history of physics. They fired alpha particles, which are positively charged particles emitted by radioactive materials, at a very thin sheet of gold foil. According to Thomson's model, the positive charge in each gold atom was spread out uniformly. The alpha particles should have passed through the foil with only very slight deflections, like bullets passing through a cloud. And most of them did exactly that. They passed straight through with barely any change in direction, but some alpha particles were deflected at large angles, and a small number bounced almost straight back toward the source. Rutherford was astonished. He later said it was as if you had fired a 15-inch artillery shell at a piece of tissue paper, and the shell came back and hit you. The only way to explain these results was to abandon the plum pudding model entirely. The positive charge in an atom could not be spread out evenly. It had to be concentrated in an incredibly small, incredibly dense core at the center of the atom. Rutherford called this core the nucleus. The atom, he concluded, was mostly empty space, a tiny, dense, positively charged nucleus at the center, with electrons somewhere in the vast emptiness surrounding it. To appreciate just how empty an atom really is, consider this analogy. If you scaled up the nucleus of a hydrogen atom to the size of a basketball and placed it at the center of a football field, the single electron would be a tiny speck somewhere in the parking lot outside the stadium. Everything between the nucleus and the electron is empty. Nothing there but fields and quantum probability. Atoms, the building blocks of everything you can see and feel, are overwhelmingly composed of nothing at all. This immediately raised a devastating problem. According to classical physics, the physics of Isaac Newton and James Clerk Maxwell that had worked so brilliantly for centuries, an electron moving around a nucleus should continuously emit electromagnetic radiation. It should lose energy with every orbit. It should spiral inward, radiating away its energy in a tiny fraction of a second and crash into the nucleus. Every atom in the universe should collapse almost instantly. Matter should not be stable, but it is. You exist. The ground beneath you is solid. Stars burn for billions of years. Something was fundamentally wrong with classical physics when applied at the atomic scale. In 1913, the Danish physicist Niels Bohr proposed a radical solution. He suggested that electrons could only occupy certain specific energy levels around the nucleus. Not any orbit, but particular allowed orbits, each with a specific, quantized amount of energy. An electron could jump from one energy level to another by absorbing or emitting a precise packet of energy, a quantum of light. But it could not exist between these levels. This explained why atoms were stable. Electrons in the lowest, allowed energy state had nowhere lower to go. They could not spiral inward because there was no allowed state closer to the nucleus. Bohr's model also explained why atoms emit and absorb light at specific frequencies, producing the characteristic spectral lines that had puzzled scientists for decades. But Bohr's model, useful as it was, still treated electrons as tiny particles moving in definite circular paths around the nucleus. It worked beautifully for hydrogen, the simplest atom with just one electron. But it failed for more complex atoms. It could not explain the spectra of helium or lithium or any atom with more than one electron. Something deeper was needed, a more fundamental theory that could describe what electrons really do inside atoms. And that theory arrived in the 1920s, and it changed everything. In 1924, a French physicist named Louis de Broglie proposed something that sounded almost absurd. He suggested that particles like electrons also behave as waves, not metaphorically, literally. Every particle, he claimed, has a wavelength associated with it. That wavelength is inversely related to the particle's momentum. Faster particles have shorter wavelengths. Slower particles have longer wavelengths. For large objects like baseballs or cars, the wavelength is so unimaginably tiny, trillions of times smaller than an atom, that wave behavior is completely undetectable. But for something as small and light as an electron, the wavelength is significant, comparable to the size of an atom. At that scale, wave behavior becomes dominant. This was confirmed experimentally by the double-slit experiment, one of the most important and most discussed experiments in the history of science. When electrons are fired one at a time at a barrier with two narrow slits, and you place a detector screen behind the barrier, each individual electron hits the screen at a single point, like a particle. But if you fire many electrons and record where each one lands, a pattern gradually emerges. Not the two bright bands you would expect if particles were simply going through one slit or the other. Instead, an interference pattern, alternating bright and dark bands. Bright bands where many electrons land, dark bands where almost none land. This is the pattern you get when waves pass through two slits and interfere with each other. Constructive interference where wave crests align, creating bright bands. Destructive interference where a crest meets a trough, cancelling out, creating dark bands. Each individual electron passing through the apparatus one at a time somehow interferes with itself. It does not go through one slit or the other. It goes through both, simultaneously, as a wave. But when it hits the detector, it arrives as a particle at a single definite point. And if you try to determine which slit the electron went through, if you place a detector at the slits to catch it in the act, the interference pattern vanishes. The electron behaves as a particle, going through one slit only. The act of observation changes the outcome. This is not a limitation of our instruments. This is a fundamental property of quantum mechanics. The electron does not have a definite trajectory between measurements. It exists in a superposition of possibilities until it is observed. In 1926, the Austrian physicist Erwin Schrödinger developed the mathematical framework that describes this behavior. The Schrödinger equation does not tell you where an electron is. It gives you a wave function, a mathematical object that encodes the probability of finding the electron at any given location. The square of the wave function at a particular point gives the probability density at that point. Not the certainty, the probability. The electron does not have a definite position until you measure it. Between measurements, it exists as a probability distribution, a cloud of possibilities spread across space. This was deeply unsettling to many physicists, including Albert Einstein himself, who famously declared that God does not play dice with the universe, but experiment after experiment confirmed that quantum mechanics was correct. At the smallest scales, the universe is genuinely probabilistic. An electron is not a tiny dot located at a precise point. It is a smear of probability, a quantum cloud. But quantum mechanics, revolutionary as it was still not the complete picture. It described how particles behave, but it did not fully explain what they are at the deepest level. For that, we need quantum field theory. Quantum field theory is the framework that combines quantum mechanics with Albert Einstein's special theory of relativity. It was developed primarily in the 1940s and 50s by Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and Freeman Dyson. And it gives us the most fundamental description of reality that we currently possess. In quantum field theory, the basic building blocks of the universe are not particles. They are fields. A field in physics is something that has a value at every point in space and time. You are already familiar with fields, even if you do not think of them that way. Temperature is a field. At every point in a room, there is a temperature value. The wind is a field. At every point in the atmosphere, the air has a speed and a direction. Gravity is a field. At every point in space, there is a gravitational influence with a specific strength and direction. Quantum field theory says the universe is permeated by fundamental quantum fields. There is an electron field that fills every point in space. There is a photon field. There is a quark field for each type of quark. For every fundamental particle in the standard model of particle physics, there is a corresponding field. These fields are everywhere, always, at every point, in every direction, throughout the entire universe. And here's the key insight, the insight that redefines what matter is. Particles are not objects that exist independently of these fields. Particles are excitations of the fields. An electron is not a tiny ball that happens to sit in the electron field. An electron is a localized vibration, a ripple, a quantized excitation in the electron field itself. Think of waves on the surface of an ocean. The ocean is the field. It is always there, filling the basin. A wave is not a separate object that exists independently of the ocean. A wave is the ocean, temporarily taking on a particular form. When the ocean is calm, there are no waves. When energy disturbs the surface, waves appear. The waves are the ocean in a state of excitation. Similarly, the electron field is always there. When it is in its lowest energy state, its ground state, there are no electrons. But when enough energy excites the field in a localized way, an electron appears. The electron is the field, vibrating in a specific quantum mode. When the excitation dissipates, the electron ceases to exist. It does not go somewhere else. It is simply no longer there. This is what an electron really is. A quantized excitation of the electron field. A bundle of energy and quantum properties that the field carries in a localized configuration. And this changes everything about how we should think about matter. The solid objects around you are not made of tiny solid components packed together. They are made of interacting quantum field excitations. Your body is not a collection of miniature parts stuck together with glue. It is a symphony of vibrating quantum fields. Now let us talk about the properties of this remarkable entity. Because even though the electron is not a tiny ball, it has very specific, precisely measured properties that govern how it interacts with the rest of the universe. The electron carries an electric charge of -1 elementary charge. This is the fundamental unit of electric charge in nature. The proton in the atomic nucleus carries +1 elementary charge. Atoms are electrically neutral because they have equal numbers of protons and electrons. The electron's charge has been measured with extraordinary precision. It is approximately 1.602 times 10 to the -19 coulombs. This charge is what drives nearly everything in your daily life. Every chemical reaction, every electrical circuit, every nerve impulse in your body depends on the movement and interaction of the electric charges carried primarily by electrons. The electron has a mass of approximately 9.109 times 10 to the -31 kilograms. That is staggeringly small. A single grain of sand has a mass roughly 1,000 trillion times greater than the mass of one electron. If you tried to gather enough electrons to weigh 1 gram, you would need more than a billion of them. One of the strangest properties of the electron is something called spin. In classical physics, spin is straightforward. A basketball spins on your finger. The Earth spins on its axis. These are physical objects rotating around a central axis. But electron spin is nothing like that. The electron has no known size, no known surface, nothing to physically rotate, and yet it possesses an intrinsic angular momentum that behaves in experiments exactly as though it was spinning. This angular momentum is quantized. It always has a value of 1/2, measured in units of the reduced Planck constant. This makes the electron a fermion. Particles with half-integer spin values are called fermions. Particles with whole integer spin, like 0 or 1 or 2, are called bosons. This distinction between fermions and bosons is one of the most important in all of physics. It determines how particles are allowed to arrange themselves, and it will become absolutely crucial when we explore why nothing in the universe ever truly makes contact with anything else. The electron's spin has only two possible measured orientations along any chosen axis: spin up and spin down. There is no in between, no gradual range, just two discrete values. Key experimental evidence came in 1922 when Otto Stern and Walter Gerlach sent a beam of silver atoms through a non-uniform magnetic field and observed the beam split into exactly two distinct paths. At the time, the result was puzzling because existing theory predicted an odd number of paths. It was not until 1925 that George Uhlenbeck and Samuel Goldsmith proposed the concept of electron spin, which finally explained the two-way splitting. The outermost electron in each silver atom had an intrinsic property with precisely two possible values: spin up and spin down. Another deeply important fact about the electron is that it appears to be a true point particle. As far as our most precise experiments can determine, the electron has no internal structure and no measurable size. Experiments at the most powerful particle accelerators, such as the Large Electron-Positron Collider at CERN, have probed the electron down to scales of roughly 10 to the negative 18 meters. At that extraordinary resolution, the electron still looks like a perfect point. No substructure has been found, no constituent parts, just a dimensionless excitation of the electron field carrying specific quantum properties. This might seem paradoxical. How can something with no physical size have mass and charge and spin? How can something that occupies no volume have such definite, measurable properties? The answer is that these properties do not require a physical size to exist. They are quantum numbers, labels describing the state of the field excitation. The electron does not need spatial extent to possess these attributes, any more than a musical note needs a physical size to have a pitch. Treating the electron as a point-like field excitation led to the development of quantum electrodynamics, known as QED, which describes how electrons interact with photons through the electromagnetic field. QED was developed primarily by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the late 1940s, and it is arguably the most precise and successful scientific theory ever constructed. The magnetic moment of the electron, a quantity describing how strongly it interacts with magnetic fields, has been measured experimentally and calculated theoretically to agree to more than 10 significant figures. That is a precision of roughly 1 part in 10 billion. It is the most accurate agreement between prediction and measurement in the entire history of science, and it is built on treating the electron as a point-like quantum field excitation. So when you hear the word electron, do not imagine a tiny ball. Picture instead a localized disturbance in a field that pervades all of space, a ripple in the quantum fabric of reality, something that has no known size yet possesses mass, charge, and spin, something that behaves as a wave when not observed, and as a particle when measured, something whose position is not defined until a measurement is made, existing instead as a probability cloud spread across space. This is what an electron really is. And understanding this is the essential first step toward understanding why you have never touched anything. Because if the building blocks of matter are not solid objects but excitations in fields, if they have no surfaces and no edges, then the entire concept of physical contact begins to dissolve. If there is no hard boundary to an electron, what would it even mean for two electrons to make contact? What would it mean for two atoms to press against each other? As we are about to discover, the answer is that they never do. They never have. And according to the laws of physics as we understand them, they never will. Every sensation of contact you have ever experienced, every moment you believed you were touching something, was something else entirely. Something created not by physical collision, but by the invisible, elegant forces of quantum fields obeying quantum rules. We have established what an electron truly is. Not a tiny sphere, not a miniature planet. A quantized excitation of the electron field. A ripple in a quantum field that pervades all of space. Something with no known size, no confirmed internal structure, yet possessing definite mass, a definite charge, and an intrinsic angular momentum we call spin. Now we need to understand how these extraordinary entities arrange themselves inside atoms. Because the architecture of the atom, the way electrons organize themselves around the nucleus, is what gives matter every property you have ever observed. Its color, its hardness, its ability to conduct electricity or heat, its chemical behavior, and most importantly for our story, its apparent solidity. The illusion that objects are solid, that surfaces exist, that things can touch, all of it traces back to how electrons live inside atoms. So let us begin by dismantling one of the most persistent and most misleading images in all of science education. The planetary model of the atom. You had seen this image countless times. A central nucleus, usually drawn as a cluster of coloured spheres, with electrons orbiting around it in neat circular or elliptical paths, like tiny planets orbiting a miniature sun. This image appears on textbook covers, on science fair posters, on the logos of physics departments and atomic energy commissions around the world. It is iconic, it is elegant, and it is profoundly wrong. Not slightly inaccurate, not a useful simplification. Profoundly, fundamentally wrong in a way that actively prevents people from understanding what atoms actually are and how they actually behave. The planetary model was a product of its time. Niels Bohr introduced it in 1913, and for a brief period, it was revolutionary. It explained why hydrogen emits light at specific frequencies. It introduced the idea of quantized energy levels, which was genuinely new and important. But within barely a decade, Bohr's model was superseded by a far more complete and far stranger theory, quantum mechanics. And quantum mechanics paints a picture of the atom that looks nothing like tiny planets circling a sun. In the quantum mechanical description, an electron inside an atom does not have a definite position at any given moment. It does not trace out a path. It does not orbit in any classical sense. Instead, the electron is described by a mathematical object called a wave function. This wave function is a solution to the Schrödinger equation, the central equation of non-relativistic quantum mechanics, developed by Austrian physicist Erwin Schrödinger in 1926. The wave function encodes everything that can be known about the electron's state. And crucially, what it tells you is not where the electron is, but where it might be found if you look. If you take the wave function at a particular point in space and square its value, you get what physicists call the probability density at that point. This is the likelihood per unit volume of detecting the electron there if you were to make a measurement. Not certainty, probability. The electron does not sit at one location waiting to be found. It exists as a spread out cloud of probability, with some regions being more likely than others, but no single region being guaranteed. When you map out this probability density in 3 dimensions around the nucleus, you get what is called an orbital. This word is crucial, and the distinction between an orbital and an orbit matters enormously. An orbit is a path, a trajectory, a line through space that an object follows. An orbital is a probability cloud, a three-dimensional map showing where the electron is most likely to be detected. It has no sharp edges, no defined boundary. It fades gradually with distance from the nucleus, the probability getting smaller and smaller, but technically never reaching exactly zero. In principle, there is a non-zero probability of finding the electron on the other side of the planet, on the other side of the galaxy, on the other side of the observable universe, but practically, the overwhelming majority of the probability is concentrated in a region a few tenths of a nanometer across, centered on the nucleus. The simplest orbital is the 1s orbital of hydrogen. This is the ground state, the lowest energy configuration of the single electron in a hydrogen atom. The 1s orbital is spherically symmetric. This means the probability of finding the electron at a given distance from the nucleus is the same in every direction. The probability is highest very close to the nucleus and decreases smoothly with distance. If you could somehow take 1 billion snapshots of the electron's position, each time finding it at a slightly different location, and then plotted all billion positions on a single image, you would see a fuzzy spherical cloud, dense near the center, fading toward the edges. No hard surface, no defined boundary, just a gradual fade from likely to unlikely. As you move to higher energy levels, the orbitals become dramatically more complex and visually stunning. The 2s orbital is still spherically symmetric, like the 1s, but it is larger and it contains a radial node. A node is a region where the probability of finding the electron drops to exactly 0. In the 2s orbital, there is a spherical shell around the nucleus where the electron will never be found. Inside this shell and outside it, the probability is non-zero, but on the shell itself, precisely 0. This is a purely quantum mechanical phenomenon with no classical equivalent. In Bohr's planetary model, there was nothing like this. Electrons just circled in fixed orbits. But in reality, the probability distribution has this strange, beautiful structure with regions of 0 probability separating regions of non-zero probability. The 2p orbitals are even more striking. They are not spherical at all. Each one has a dumbbell shape, with 2 lobes of probability extending in opposite directions from the nucleus, separated by a nodal plane where the electron is never found. There are 3 2p orbitals, oriented along the 3 perpendicular spatial axes. One along the x-axis, one along the y-axis, one along the z-axis. These shapes are not arbitrary. They emerge naturally as solutions to the Schrödinger equation for the electrostatic potential created by the nucleus. The mathematics dictates the shapes, and the shapes, in turn, dictate how atoms interact with each other, how they bond, how they form molecules, how they create the materials and substances that make up the physical world. The d orbitals, which appear at the 3rd energy level and above, are even more elaborate. Some look like 4-leaf clovers with 4 lobes of probability arranged symmetrically. Others resemble a dumbbell surrounded by a donut-shaped ring. The f orbitals, which appear at the 4th energy level and above, are more complex still, with intricate multi-lobed shapes that are difficult to visualize but mathematically precise. Each of these orbital shapes is described by a specific set of quantum numbers. There are 4 quantum numbers, and together they completely describe the state of an electron in an atom. Understanding these numbers is essential because they are the rules of the game. They determine how electrons fill up the available space around a nucleus, And that filling pattern is what gives every element its unique identity. The first is the principal quantum number, designated by the letter N. This determines the energy level and the general size of the orbital. It can take any positive integer value, 1, 2, 3, 4, and so on. Higher values of N mean higher energy and a larger orbital, meaning the electron's probability cloud extends farther from the nucleus. The principal quantum number essentially tells you which shell the electron is in. The second is the angular momentum quantum number, designated by the letter L. This determines the shape of the orbital. It can take any integer value from 0 up to n-1. When L equals 0, you get an s orbital, which is spherical. When L equals 1, you get a p orbital, which is dumbbell-shaped. When L equals 2, you get a d orbital with its more complex geometry. When L equals 3, you get an f orbital. Each value of L gives a different orbital shape with different angular properties. The third is the magnetic quantum number, designated m sub L. This determines the orientation of the orbital in space. It can take any integer value from negative L to positive L. For a p orbital, where L equals 1, the magnetic quantum number can be -1, 0, or +1. This gives 3 p orbitals, each oriented along a different axis. For a d orbital, where L equals 2, there are 5 possible orientations. For an f orbital, 7. Each orientation represents a distinct orbital pointing in a distinct direction. The fourth and final quantum number is the spin quantum number, designated m sub s. This is the quantum number associated with the electron's intrinsic spin. It can take only 2 values, positive 1/2 or negative 1/2. Spin up or spin down, nothing else. No intermediate values, just these 2. This binary nature of electron spin turns out to have consequences so vast, so far-reaching, that it is difficult to overstate them. Because it leads directly to the single most important organizational principle in all of atomic physics, the Pauli exclusion principle. In 1925, the Austrian physicist Wolfgang Pauli, who was only 25 years old at the time, proposed a rule that seemed almost deceptively simple. No 2 identical fermions in a system can occupy the same quantum state simultaneously. Since electrons are fermions, this translates to a very specific constraint inside atoms. No 2 electrons in the same atom can have the same set of all 4 quantum numbers. If 2 electrons share the same principal quantum number, the same angular momentum quantum number, and the same magnetic quantum number, meaning they are in the same orbital, then they must have different spin quantum numbers. One must be spin up and the other must be spin down. If both spin states are already taken, that orbital is full. No additional electron can enter it. Period. The quantum rules forbid it. This might sound like a minor technical detail. A bookkeeping rule for tracking electrons. It is not. The Pauli exclusion principle is one of the most consequential laws in the entire universe. Without it, all electrons in any atom would simply collapse into the lowest energy orbital, the 1s orbital. Every atom, regardless of how many electrons it contained, would have the same electron configuration. Hydrogen with 1 electron and uranium with 92 electrons would behave identically. There would be no periodic table, no chemistry, no different materials, no molecules, no proteins, no DNA, no life, no you. The Pauli exclusion principle is the reason the periodic table exists. It is the reason carbon behaves differently from oxygen, why gold is different from iron, why the universe contains the staggering diversity of substances and materials that it does. Let me walk through how this works because it is genuinely beautiful. Hydrogen has 1 electron. That electron goes into the lowest available energy state, the 1s orbital. Simple enough. Helium has 2 electrons. The first goes into the 1s orbital with spin up. The second also goes into the 1s orbital, but it must have spun down because the spin-up state is already occupied. Now the 1s orbital is completely full. Both possible spin states are taken. No more electrons can fit. The first shell is closed. This is why helium is a noble gas. Its outermost shell is completely full. It has no need to share electrons with other atoms. No tendency to form chemical bonds. It is chemically inert, satisfied with its complete electron configuration. Helium barely interacts with anything. It does not combust. It does not corrode. It simply exists, stable and unreactive, because the Pauli exclusion principle has filled its only shell to capacity. Lithium has 3 electrons. 2 fill the 1s orbital completely, just like in helium. The third electron cannot join them. The 1s orbital is full. Both spin states are occupied. The Pauli exclusion principle absolutely forbids a third electron from entering that orbital. So the third electron is forced into the next available orbital, the 2s. This orbital is at a higher energy level. It is farther from the nucleus. The electron sitting in it is less tightly bound, more exposed, more available for interaction with other atoms. This is why lithium is a highly reactive metal. It has 1 loosely held outer electron that it readily gives up in chemical reactions. The dramatic difference in behavior between helium and lithium, one a completely inert gas and the other a violently reactive metal, comes down entirely to the Pauli exclusion principle, forcing that third electron into a higher energy orbital. Carbon has 6 electrons. 2 fill the 1s orbital, 2 fill the 2s orbital. The remaining 2 occupy 2 of the 3 available 2p orbitals. Carbon's 4 outer electrons, 2 in the 2s and 2 in the 2p, give it the ability to form 4 chemical bonds simultaneously. This extraordinary bonding versatility is the foundation of all organic chemistry. Carbon can link to other carbon atoms in chains, rings, branches, and 3-dimensional frameworks. It can bond to hydrogen, oxygen, nitrogen, and dozens of other elements. The complexity of carbon-based chemistry, the vast diversity of organic molecules that carbon can form, is ultimately a consequence of the Pauli exclusion principle dictating carbon's electron configuration. Every living thing on Earth is based on carbon chemistry. The proteins in your muscles, the DNA that carries your genetic information, the lipids in your cell membranes, the carbohydrates that fuel your metabolism, all of them are carbon-based molecules. And all of them exist because the Pauli exclusion principle forces carbon's 6 electrons into a configuration that allows 4 bonds. Without the exclusion principle, carbon would not have this configuration. Organic chemistry would not exist. Life as we know it would be impossible. The pattern continues across the entire periodic table. Each element has its electrons arranged in a specific configuration, dictated by the quantum numbers and the Pauli exclusion principle. Electrons fill available orbitals in a systematic way, generally starting with the lowest energy states and working upward. When one shell or subshell is full, the next electron must go into a higher energy state. The specific configuration of the outermost electrons, the valence electrons, determines how each element interacts chemically with others. Iron has 26 electrons. The way those electrons fill the various orbitals, particularly the 3d orbitals, gives iron its remarkable magnetic properties. The 3d subshell in iron is partially filled. Some of the d orbitals contain only one electron rather than the maximum 2. These unpaired electrons have aligned spins, creating a net magnetic moment. When billions of iron atoms are packed together in a crystal, these individual magnetic moments can align with each other, producing the macroscopic magnetism we observe. The ability of iron to be magnetized, the reason a compass needle points north, the reason magnets stick to your refrigerator, all of it traces back to the Pauli exclusion principle and how it fills iron's electron orbitals. Copper has 29 electrons. Its electron configuration leaves one electron in the outermost 4s orbital, loosely bound and free to move. In a piece of copper wire, these outermost electrons are not bound to any particular atom. They form what physicists call a sea of delocalized electrons, flowing freely through the metal lattice. When you apply a voltage across a copper wire, these free electrons drift in response, creating an electric current. This is why copper is one of the best conductors of electricity. Every wire in your house, every circuit in your phone, every electrical cable connecting power plants to cities relies on the fact that the Pauli exclusion principle gives copper an electron configuration with one loosely held outer electron. Gold has 79 electrons. Its electron configuration is complex, involving filled subshells that extend deep into the atom. But here is something remarkable. The innermost electrons in gold are held so close to the massive nucleus, with its 79 protons worth of positive charge, that they move at speeds approaching a significant fraction of the speed of light. At these speeds, relativistic effects become important. The inner electrons effectively become more massive due to their speed, which causes them to orbit slightly closer to the nucleus than non-relativistic physics would predict. This contraction of the inner orbitals has a cascading effect that shifts the energy levels of the outer electrons. The result is that gold absorbs blue light more strongly than other visible wavelengths and reflects the remaining light with a warm, yellowish tone. The distinctive color of gold, the reason it looks different from silver or platinum, is ultimately a consequence of quantum mechanics combined with special relativity, operating on an electron configuration dictated by the Pauli exclusion principle. Even the beauty of a gold ring on your finger traces back to these quantum rules. Now, the Pauli exclusion principle does not just determine how electrons fill orbitals within individual atoms. It also governs profoundly what happens when atoms come close to each other. This is where the exclusion principle connects directly to the question at the heart of our story: why nothing ever touches. But the Pauli exclusion principle does not only determine how electrons fill orbitals within individual atoms, it also governs what happens when atoms come close to each other. And this is where the exclusion principle connects directly to the question at the heart of our story: why nothing ever touches. When two atoms approach each other, their electron clouds begin to overlap. And when that happens, both the electromagnetic repulsion between their negatively charged electrons and the Pauli exclusion principle refusing to let identical fermions share quantum states begin to push back. Together, these two effects create an effective barrier between atoms, a barrier that no amount of gentle pushing can overcome, a barrier that is responsible for every sensation of solidity you have ever experienced. But exactly how this barrier works, exactly what is happening when your hand presses against a table and feels resistance, exactly what is occurring atom by atom in that tiny gap between your skin and the surface, that is what we need to examine closely. Because when you understand precisely what is happening in that gap, you will understand why nothing in the universe has ever physically contacted anything else. You press your hand flat against a table. You feel the surface beneath your palm, solid, firm, unyielding. You push down and the table pushes back with equal force. You can feel the grain of the wood, the smoothness of the finish, the coolness of the material. Every signal your nervous system sends to your brain confirms the same message. Your hand is in contact with the table. The atoms of your skin are meeting the atoms of the wood. Two surfaces are pressed together. They are not. What is actually happening beneath your palm is something far more interesting, far more subtle, and far more beautiful than two surfaces meeting. No atom in your hand has made physical contact with any atom in that table. None of them are even close to making contact. And no matter how hard you press, no matter how much force you apply, they never will. Let us look at exactly what happens, atom by atom, when your hand approaches that tabletop. Your skin is made of cells. Those cells are made of molecules. Those molecules are made of atoms. And those atoms, as we have now established, consist of a tiny dense nucleus, surrounded by an extended cloud of electron probability. The outermost atoms in the surface layer of your skin have electron clouds that extend outward, fading gradually with distance but never reaching a hard edge. There is no boundary, no shell, no wall, just a probability distribution that gets weaker and weaker the farther you go from the nucleus. The table surface is the same. Wood is made of cellulose and lignin molecules, which are themselves made of carbon, hydrogen, oxygen, and other atoms. Each of those atoms has its own electron cloud, its own fuzzy probability distribution extending outward from its nucleus. The outermost atoms on the table's surface have electron clouds that extend upward into the space above the table. As your hand descends toward the table, something begins to happen long before any intuitive notion of contact. The electron clouds of your outermost skin atoms and the electron clouds of the outermost table atoms start to overlap. Not violently, not suddenly, gradually. The probability distributions begin to extend into the same region of space. And the moment this overlap begins, two powerful effects engage simultaneously. The first is electromagnetic repulsion. The electrons in your skin atoms carry a negative electric charge. The electrons in the table atoms also carry a negative electric charge. This is a fundamental law of electromagnetism. Like charges repel. The closer two negative charges get to each other, the stronger the repulsive force between them. As the electron clouds begin to overlap, billions upon billions of negatively charged electrons in your hand are getting close to billions upon billions of negatively charged electrons in the table. The cumulative electromagnetic repulsion is enormous. It pushes back against your hand with a force that increases rapidly as the distance between the electron clouds decreases. The second effect is the Pauli exclusion principle. The electrons in your hand and the electrons in the table are identical fermions. They are the same type of particle, with the same mass, the same charge, the same spin magnitude. As the electron clouds overlap, these identical fermions are increasingly being asked to occupy the same quantum states in the same region of space. The Pauli exclusion principle forbids this absolutely. No two identical fermions can share the same quantum state. As the overlap increases, electrons are forced into progressively higher energy configurations to avoid violating this principle. This costs energy. And that energy cost manifests as a powerful resistance to further compression. A quantum mechanical pushback that grows stronger and stronger the more you try to squeeze the clouds together. These two effects, the electromagnetic repulsion between negatively charged electron clouds and the Pauli exclusion principle, preventing identical fermions from sharing quantum states, work together to create an effective barrier. This barrier is what you feel when your hand meets the table. Not matter meeting matter, not surface pressing against surface, but fields resisting fields. Quantum rules forbidding compression. Electromagnetic force pushing back against your push. The atoms in your hand and the atoms in the table never get closer than approximately 1 angstrom from each other. 1 angstrom is 1/10,000,000th of a meter, about 1/10th of a nanometer. This is the typical equilibrium distance, at which the repulsive forces from electromagnetic interaction and the Pauli exclusion principle balance against any attractive forces between atoms. Closer than this distance, repulsion dominates overwhelmingly. Farther than this, attractive forces like van der Waals interactions gently pull atoms toward each other. At this equilibrium distance, there is a gap between your hand and the table. A gap filled with nothing but electromagnetic fields and quantum probability. But this gap is so astonishingly small compared to anything your senses can detect that your brain interprets the interaction as direct contact. Your nervous system has no way to distinguish between actual physical contact, if such a thing even made sense at the quantum level, and the electromagnetic repulsion of overlapping electron clouds. To your brain, they are identical. The sensation of touching the table is created entirely by electromagnetic forces and quantum exclusion effects. It always has been. Every time you have ever touched anything in your entire life, this is what was actually happening. Let me walk through more examples because this principle is universal. It applies to every single physical interaction you have ever experienced. When you sit in a chair, you are not resting on a surface. The electron clouds of the atoms in your body and the electron clouds of the atoms in the chair are interacting electromagnetically. The repulsive force created by this interaction supports your entire weight. You are, in a very literal sense, hovering above the chair. The gap is incredibly small, on the order of angstroms, but it is real. The electromagnetic force generated by the interaction of electron clouds is what holds you up. If someone asks what is supporting you when you sit, the true answer is electromagnetism and the Pauli exclusion principle, not the physical surface of the chair. When you walk across a room, your feet never make contact with the floor. Every step you take is cushioned by the electromagnetic interaction between the electron clouds in the soles of your feet and the electron clouds in the floor's surface. The friction that keeps you from slipping, the resistance that propels you forward, all of it arises from electromagnetic forces between overlapping electron clouds. At no point do atoms in your feet come into physical contact with atoms in the floor. When you pick up a glass of water, your fingers do not grip the glass in the way you imagine. The electron clouds in your fingertip atoms interact with the electron clouds in the glass atoms through electromagnetic forces. These forces create enough resistance, enough friction for you to hold the glass securely. But no atom in your finger has ever met an atom in that glass. The grip is electromagnetic. The hold is quantum mechanical. When you type on a keyboard, each keystroke is an electromagnetic event. Your fingertip approaches the key, the electron clouds interact, and the resulting force depresses the key. When you feel the key click, that tactile feedback is electromagnetic force transmitted through the key mechanism to your fingertip, where it excites nerve endings through more electromagnetic interactions. Every aspect of the experience, from the initial press to the sensation of the click, is mediated by electromagnetic fields and quantum exclusion effects. When you hug another person, no matter how tightly you hold them, not a single atom in your body makes physical contact with a single atom in theirs. The warmth you feel is infrared electromagnetic radiation passing between your bodies. The pressure of the embrace is electromagnetic repulsion between overlapping electron clouds. The sensation of closeness, the comfort of physical presence, the feeling of another person's body against yours, all of it is created by fields interacting with fields. It is not less real for being electromagnetic. If anything, it is more remarkable. The forces that create the experience of a hug are the same forces that hold atoms together, that give stars their structure, that govern the behavior of matter across the entire universe. Now, let me address friction in more detail, because friction seems like the strongest evidence that things make physical contact. When you rub your hands together, you can feel them catching against each other. You feel roughness or smoothness. Heat is generated. Surely this means atoms are grinding against atoms, surfaces scraping against surfaces. They are not. Friction at the atomic level is an electromagnetic phenomenon. When two surfaces slide against each other, the atoms on one surface come close to the atoms on the other. Their electron clouds interact. Temporary electromagnetic attractions form between nearby atoms through what are called van der Waals forces. These are weak electromagnetic interactions that arise because the electron clouds of atoms are constantly fluctuating. At any given instant, the cloud might be slightly denser on one side of the atom than the other, creating a temporary imbalance of charge. This temporary imbalance can induce a complementary imbalance in a neighboring atom, creating a brief attractive force between them. As two surfaces slide past each other, these temporary electromagnetic bonds form and break millions of times per second across billions of atoms. Each time one of these bonds forms, it takes a little energy to break it. That energy is released as heat. This is why your hands get warm when you rub them together. Not because atoms are physically grinding, but because electromagnetic bonds between electron clouds are continuously forming and snapping, and each snap releases a small amount of energy as thermal vibration. The rougher a surface is, the more its atoms protrude at irregular angles, creating more opportunities for electron cloud interactions with a passing surface. This is why rough surfaces have more friction than smooth ones. A polished surface has atoms arranged so uniformly that fewer electron cloud interactions occur as another surface slides across it. But even the smoother surface still generates some friction because the electron clouds always interact electromagnetically. Friction is, at its core, an electromagnetic phenomenon, not a contact phenomenon. Here is another common experience that seems to require physical contact: catching a ball. When a ball hits your hand, you feel the impact. The ball decelerates. Your hand absorbs the momentum. It seems obvious that the ball has struck your hand, that atoms have collided. But what actually happened is this. As the ball approached your hand at speed, the electron clouds on the ball's surface approached the electron clouds on your hand's surface. The electromagnetic repulsion between these clouds generated an enormous force over an extremely short distance. This force decelerated the ball and accelerated your hand slightly. The kinetic energy of the ball was transferred to your hand through electromagnetic field interactions. At no point during the catch did any atom in the ball physically meet any atom in your hand. The entire exchange of momentum and energy occurred through field interactions across the tiny but real gap between the electron clouds. This applies to everything. A hammer striking a nail, a bat hitting a ball, a car colliding with a wall. In every one of these cases, the transfer of force and energy happens through electromagnetic interactions between electron clouds. The atoms involved never come into physical contact. They interact through fields, always through fields. Even the concept of a surface itself is misleading. When you look at a table, you see a flat, solid surface. But at the atomic level, there is no flat surface. There is no surface at all in the usual sense. There is a layer of atoms, each one a fuzzy probability cloud, with no hard edge. The apparent surface is actually a boundary where the probability of finding electrons drops below a threshold that our senses interpret as empty space. Your eyes see a sharp edge because photons, particles of light, interact with the outermost electron clouds and bounce back toward your eyes. But those electron clouds have no hard boundary. They fade gradually. The surface you see is an electromagnetic interaction between photons and electron clouds, not the edge of a physical object. When your hand rests on the table, the apparent flatness of the table's surface is really a vast landscape of electron probability clouds, each one centered on an atom in the wood. Your hand's electron clouds interact with this landscape through electromagnetic forces and the Pauli exclusion principle. The result feels like one flat surface pressing against another. But at the atomic level, it is two fuzzy landscapes of probability interacting through fields across a tiny gap. Let us also think about what happens inside solid objects, because the same principles apply there. The atoms within a solid are not stacked together like bricks in a wall, physically pressing against each other. They are held in a lattice structure by electromagnetic forces between their electron clouds. Each atom in a crystal lattice sits at an equilibrium position where the attractive forces pulling it toward its neighbors balance the repulsive forces pushing it away. The attractive forces come from chemical bonds, which are themselves electromagnetic in nature. The repulsive forces come from the electromagnetic repulsion between electron clouds and the Pauli exclusion principle. The atoms oscillate around their equilibrium positions due to thermal energy. At room temperature, atoms in a solid vibrate back and forth billions of times per second. But even at the extremes of these vibrations, the atoms never make contact with their neighbors. They are always separated by the electromagnetic and quantum mechanical barrier. The rigidity of a solid, its resistance to being squeezed or stretched, is maintained by these field interactions, not by atoms physically pressing against each other. This is true of your own body. The atoms in your bones do not physically touch each other. They are held in a crystalline lattice of calcium phosphate by electromagnetic bonds between electron clouds. The atoms in your muscles interact through electromagnetic forces as protein filaments slide past each other during contraction. Your neurons fire because ions, which are atoms with missing or extra electrons, are propelled through electromagnetic channels by electric fields. The DNA in your cells is held in its iconic double helix shape by hydrogen bonds, which are electromagnetic interactions between the electron clouds of nitrogen, oxygen, and hydrogen atoms on complementary base pairs. Every single biological process in your body, from the beating of your heart to the firing of your synapses to the replication of your DNA, is mediated entirely by electromagnetic forces and quantum mechanical effects. Nothing inside you physically contacts anything else inside you. You are not a machine made of parts that mesh together. You are a coherent arrangement of quantum field excitations interacting through electromagnetic fields and governed by the Pauli exclusion principle. You are held together not by physical contact, but by the same forces that hold atoms together, that hold molecules together, that hold stars together. This is not a technicality. This is not a philosophical distinction without practical significance. This is the actual physical reality of how matter works. And it has been confirmed by every experiment ever conducted at the atomic and subatomic scale. Quantum mechanics and quantum electrodynamics are the most precisely tested theories in the history of science. Their predictions have been confirmed to accuracies of parts per billion and beyond. The description of matter as interacting quantum field excitations mediated by electromagnetic forces is not speculative. It is not a hypothesis. It is established, verified physics. Let me also address chemical reactions because these might seem like the ultimate form of atoms making contact. In a chemical reaction, atoms rearrange, bonds break, and new bonds form. Molecules come apart and recombine into different molecules. Surely at this level, atoms must be meeting and interacting in some direct physical way. When a chemical bond forms, atoms do not make contact and stick together. Their electron clouds overlap and reshape into a new configuration, a molecular orbital that has lower total energy than the two separate atoms. The nuclei remain separated at a distance where the attractive and repulsive electromagnetic forces balance. The bond exists because of how the quantum fields of the two atoms interact at this equilibrium distance, not because of physical contact between their constituents. Every chemical bond in existence, from the bonds holding together a molecule of water to the bonds forming the DNA in your cells, is an electromagnetic rearrangement of electron probability clouds, not a mechanical attachment. Even when bonds break during a chemical reaction, what happens is not atoms pulling apart like two objects separating. The electron cloud configuration shifts. Energy is absorbed or released. The probability distribution changes shape. The molecular orbital transforms into separate atomic orbitals or into new molecular orbitals with different partners. The entire process is a rearrangement of quantum fields, not a mechanical assembly or disassembly of physical parts. Consider combustion, one of the most common chemical reactions. When wood burns, the carbon and hydrogen atoms in the wood react with oxygen molecules from the air. What happens is not atoms colliding with each other in some violent crash. Oxygen molecules approach the wood molecules. Their electron clouds interact electromagnetically. When the conditions are right, when enough thermal energy is present to overcome the activation energy barrier, the electron clouds rearrange. Old molecular orbitals dissolve and new ones form. Carbon atoms that were bonded to other carbon atoms and to hydrogen atoms in the wood now find themselves in lower energy configurations bonded to oxygen atoms, forming carbon dioxide and water. The energy difference between the old configuration and the new one is released as heat and light. This is fire, and at no point during the entire process does any atom physically meet any other atom. The same is true for every chemical reaction in the universe. Photosynthesis, respiration, digestion, rust, fermentation, explosions. Every single one is a rearrangement of electron clouds into new configurations mediated by electromagnetic forces and constrained by the Pauli exclusion principle. No physical contact required, none occurring. This understanding even extends to the most extreme environments. Inside the cores of stars, hydrogen nuclei undergo nuclear fusion. They combine to form helium, releasing enormous amounts of energy. This might seem like the ultimate example of things making contact, nuclei merging together, but even here the interaction is mediated by fields, not by physical contact. The two hydrogen nuclei must overcome the electromagnetic repulsion between their positive charges. This requires temperatures of millions of degrees, giving the nuclei enough kinetic energy for their quantum wave functions to overlap significantly at extremely short distances. At a distance of about 1 femtometer, 1 quadrillionth of a meter, the strong nuclear force, which is mediated by gluon fields, takes over. The nuclei do not bump into each other like billiard balls and stick. Their wave functions overlap. The strong force field dominates the interaction, and the nuclei merge into a new configuration. It is a field interaction through and through. So here is the truth, stated plainly. Nothing in the universe has ever physically touched anything else. Not your hand and the table, not your feet and the ground, not a bat and a ball, not two lovers in an embrace, not hydrogen nuclei fusing in the core of a star. Every interaction, at every scale, in every context, is mediated by quantum fields, electromagnetic forces, and the Pauli exclusion principle create the sensation of contact. They create the experience of solidity. They create the feeling of touch, but actual physical contact, in the classical sense of two surfaces meeting, two objects pressing together, two particles colliding, does not occur. It cannot occur. The quantum rules that govern matter make it impossible, and yet the world feels solid. The table supports your hand. The floor holds you up. Objects have shapes and textures and temperatures. The experience is vivid and rich and utterly convincing. You will go through your entire life feeling as though you are touching things, picking things up, holding things, pressing against things, and every single one of those experiences will be an electromagnetic interaction between quantum field excitations governed by the Pauli exclusion principle. This is not a failure of your senses. Your senses are doing exactly what they evolved to do, which is to help you navigate the world at the scale at which you live. At human scales, the electromagnetic forces and quantum exclusion effects that mediate all interactions are so reliable, so consistent, so overwhelmingly strong that they are indistinguishable from physical contact. Evolution did not need to give you the ability to perceive quantum field interactions. It needed to give you the ability to avoid dangers, find food, and interact with objects. For those purposes, the sensation of contact is a perfect approximation. It is an illusion, yes, but it is an extraordinarily useful one. The deeper question, the one that keeps physicists awake at night, is what this tells us about the nature of reality. If nothing ever touches, if all our sensory experiences are electromagnetic approximations of a quantum mechanical reality we cannot directly perceive, what does that mean about the world we think we know? What does it mean about the relationship between what is real and what we experience? Those are the questions we are going to explore next, because the implications of what we have discovered go far beyond the physics of atoms. They reach into the deepest questions about what matter is, what experience is, and what it means to be a conscious being made of quantum fields, living in a universe held together by forces that never allow anything to truly physically touch. We've arrived at a remarkable place. We started with a simple question about what an electron is, and we have ended up dismantling the most basic assumption most people hold about the physical world: the assumption that things touch. We have seen that electrons are not tiny balls, but excitations of a quantum field. We have seen that atoms are mostly empty space, their structure governed by probability clouds, and the Pauli exclusion principle. We have seen that every sensation of contact you have ever experienced is actually electromagnetic repulsion between electron clouds combined with the quantum mechanical resistance of identical fermions, refusing to share the same state. Nothing has ever touched anything. Now, let us think carefully about what this means, not just for physics, but for our understanding of reality itself, for the nature of experience, and for the extraordinary fact that beings made of quantum fields have somehow become capable of understanding the quantum fields they are made of. Let us begin with the mechanism of interaction itself. We have said that electromagnetic forces mediate the sensation of contact, but how exactly does the electromagnetic force work between two electron clouds? What is happening in that tiny gap between your hand and the table? In classical physics, the answer seems straightforward. Charged particles create electric fields around themselves. Other charged particles respond to those fields. The negatively charged electrons in your hand create an electric field that pushes against the negatively charged electrons in the table. This description is accurate as far as it goes. But quantum field theory gives us a deeper and more precise picture. In quantum electrodynamics, the quantum field theory of electromagnetism, the force between two charged particles is described through the exchange of virtual photons. Now, this requires careful explanation because virtual photons are one of the most misunderstood concepts in physics. A virtual photon is not a real photon. It is not a particle of light zipping back and forth between two electrons like a tennis ball being volleyed between players. You cannot detect a virtual photon with any instrument. You cannot see it. You cannot measure its position or trajectory. It does not exist as an independent particle traveling through space. A virtual photon is a mathematical description of how the electromagnetic field transmits influence between charged particles. It emerges from the equations of quantum electrodynamics as the fundamental mechanism by which electromagnetic interactions occur. When two electrons repel each other, the calculation involves summing over all possible virtual photon exchanges between them. Each possible exchange contributes to the total force. The sum of all these contributions gives the precise electromagnetic force that we observe. The reason we call them virtual rather than real is that they do not satisfy the normal energy-momentum relationship that real photons obey. A real photon, a genuine particle of light, always travels at the speed of light and has zero rest mass. Virtual photons can carry any combination of energy and momentum, including combinations that would be impossible for real particles. They are allowed to do this because they exist only for extremely brief durations, governed by the Heisenberg uncertainty principle. The uncertainty principle says that the more precisely you constrain the time interval during which something happens, the less precisely you can constrain its energy. Virtual photons exist for such vanishingly short times that their energy can fluctuate dramatically, allowing them to mediate forces in ways that real photons cannot. This might sound like an abstract mathematical trick, but it produces real, measurable consequences. The force between two charged particles, calculated using virtual photon exchange matches experimental measurements with astonishing precision. The magnetic moment of the electron, calculated using quantum electrodynamics with virtual photon contributions, agrees with experiment to better than 1 part in 10 billion. This is not a rough approximation. This is the most precise agreement between theory and measurement in the history of science. Virtual photons may be strange, but the framework that uses them describes a reality with extraordinary accuracy. So when your hand rests on a table, what is happening in that tiny gap between the electron clouds can be described as an enormously complex exchange of virtual photons between the electrons in your skin and the electrons in the wood. Billions of trillions of electrons interacting through the electromagnetic field, each interaction involving the continuous exchange of virtual photons. The cumulative effect of all these exchanges is the macroscopic force you feel as the solidity of the table. The sensation of pressing your palm against a flat, firm surface is the collective result of an astronomical number of virtual photon exchanges happening simultaneously across the entire area of contact. This framework also explains something that might otherwise seem mysterious: how forces can act across empty space. In the classical picture, this was called action at a distance, and it troubled physicists for centuries. How can one charged particle push another without anything connecting them? How does the force get transmitted across the gap? Quantum field theory answers this definitively. The force is transmitted by the field. The electromagnetic field fills all of space. Virtual photon exchange is the quantum mechanical description of how this field carries influence from one charged particle to another. There is no empty gap. The field is always there, connecting everything. Now let us reconsider chemical bonds through this deeper lens. In the previous sections, we discussed how chemical bonds form when electron clouds overlap and find lower energy configurations. But what does that really mean in terms of fields and forces? When two hydrogen atoms approach each other, each one brings a single electron in a 1s orbital, a spherical probability cloud centered on its nucleus. As the atoms get closer, these two probability clouds begin to overlap. The electrons, which were previously each associated with one nucleus, now find themselves in the vicinity of two nuclei. The electromagnetic attraction between each electron and both nuclei creates a new situation. The electrons can now exist in a molecular orbital that extends across both nuclei simultaneously. There are two possible molecular orbitals that can form. One is the bonding orbital, where the electron probability is concentrated in the region between the two nuclei. This concentration of negative charge between the two positive nuclei pulls them together. The energy of this configuration is lower than the energy of the two separate atoms. This is the covalent bond. The atoms are held together not by physical contact, but by the electromagnetic attraction between the positively charged nuclei and the negatively charged electron cloud that now spans both of them. The other possible molecular orbital is the antibonding orbital, where the electron probability is concentrated outside the region between the nuclei, with a node, a region of zero probability between them. In this configuration, there is no concentration of negative charge pulling the nuclei together. The energy is higher than the separated atoms. This configuration does not form a stable bond. The formation of a hydrogen molecule is not two balls sticking together. It is the reshaping of quantum probability distributions into a new configuration that minimizes the total energy. The electron clouds merge. The wave functions combine. The electromagnetic field between the two nuclei and the shared electrons reaches a state of lower energy than the alternative. The bond length, roughly 74 picometers for molecular hydrogen, is the distance at which this energy minimum occurs. Push the nuclei closer and the electromagnetic repulsion between the two positive charges increases along with the Pauli exclusion pressure from the overlapping electron clouds. Pull them farther apart and the stabilizing overlap of the bonding molecular orbital decreases. The equilibrium distance is where these competing effects balance. This same principle governs every chemical bond in existence. Carbon-carbon bonds, carbon-oxygen bonds, nitrogen-hydrogen bonds, the peptide bonds that link amino acids into proteins, the phosphodiester bonds that hold DNA strands together. Every single bond is an electromagnetic phenomenon. A reshaping of electron probability clouds into a configuration that minimizes energy. Not a physical joining. Not a mechanical attachment. A quantum field rearrangement. The diversity of chemical bonds is extraordinary. Single bonds involve the sharing of one pair of electrons. Double bonds involve two pairs. Triple bonds involve three. Ionic bonds form when one atom transfers an electron to another, creating positive and negative ions that attract each other electromagnetically. Metallic bonds involve a sea of delocalized electrons shared among many atoms simultaneously. Hydrogen bonds, which are crucial for the structure of water and the shape of proteins and DNA, are weak electromagnetic attractions between a hydrogen atom bonded to an electronegative atom and a lone pair of electrons on a nearby electronegative atom. All of these bonds, every variety, every strength, every configuration, are electromagnetic interactions between electron clouds. The enormous diversity of materials in the universe, from diamond to water to silk to steel, arises from different arrangements of atoms held together by different configurations of electron clouds interacting through the electromagnetic field. And not a single one of these arrangements involves physical contact between atoms. Every material you have ever encountered is held together by fields, not by stuff pressing against stuff. Let us now think about what this means for our experience of the world. Because our sensory experience of matter is extraordinarily rich, you do not just feel that something is there. You feel texture, smoothness, roughness, warmth, cold, softness, hardness, wetness, dryness. Each of these qualities feels fundamentally different. And each of them is created by a different pattern of electromagnetic interaction between the electron clouds in your skin and the electron clouds of whatever you are feeling. When you run your fingers across polished marble, the smoothness you perceive comes from the extreme regularity of the surface at the atomic level. The atoms on the marble's surface are arranged in a highly ordered crystalline structure. As your fingertip slides across this surface, the electromagnetic interactions between your skin's electron clouds and the marble's electron clouds are nearly uniform. The force is consistent. There are no sudden changes in resistance. Your brain interprets this uniformity as smoothness. When you run your fingers across sandpaper, the experience is dramatically different. The surface is covered with abrasive particles arranged irregularly. At the atomic level, the surface is jagged, with electron clouds protruding at varying angles and heights. As your fingertip slides across, the electromagnetic interactions vary rapidly. Regions of stronger interaction alternate with regions of weaker interaction. Your fingertip encounters constantly changing resistance. Your brain interprets this variation as roughness. Temperature perception is also electromagnetic. When you touch something cold, thermal energy flows from your hand to the object. This happens because the atoms in your hand are vibrating more energetically than the atoms in the cold object. When the electron clouds of your skin interact electromagnetically with the electron clouds of the cold surface, some of the vibrational energy in your skin atoms is transferred to the less energetic atoms in the object. Your nerve endings detect this energy outflow, and your brain interprets it as cold. When you touch something warm, the process reverses. Energy flows from the warm object into your skin. Your nerve endings detect this energy inflow, and your brain interprets it as warmth. All of this happens through electromagnetic interactions between electron clouds. No physical contact is required or involved. The hardness or softness of a material is determined by how strongly its atoms resist being displaced from their equilibrium positions. In a hard material like diamond, the atoms are locked into a rigid lattice by extremely strong covalent bonds. The electromagnetic forces holding each carbon atom in place are immense. When you press your finger against diamond, the electron clouds in the diamond resist deformation. The atoms barely move. Your brain interprets this strong resistance as hardness. In a soft material like clay, the bonds between atoms are weaker or more easily disrupted. When you press your finger against clay, the atoms shift more readily. The electron clouds reorganize with less resistance. Your brain interprets this yielding as softness. In both cases, the experience is entirely electromagnetic. In 1967, the physicists Freeman Dyson and Andrew Leonard published a landmark proof that the stability of matter, the fact that a block of iron does not collapse into a point, depends critically on the Pauli exclusion principle. They showed that if electrons were bosons rather than fermions, if they did not obey the exclusion principle, the energy of matter would scale not linearly with the number of particles, but as the 7/5 power. Matter would be catastrophically unstable. It would implode. The exclusion principle prevents this by forcing electrons into higher and higher energy orbitals, rather than allowing them all to pile into the lowest energy state. This is what creates the extended electron clouds that give atoms their size. Without the exclusion principle, atoms would be far smaller. Matter would be far denser. The familiar properties of solidity, rigidity, and resistance to compression would not exist. The world you know exists because electrons are fermions, because they obey the Pauli exclusion principle, because they refuse to share quantum states. Even the sensation of wetness is electromagnetic. When you dip your hand in water, the water molecules, each one a small arrangement of one oxygen atom and two hydrogen atoms bonded together at an angle of about 104.5 degrees, interact with the molecules on your skin through hydrogen bonds and van der Waals forces. Both of these are electromagnetic interactions between electron clouds. The water molecules slide across your skin, forming and breaking temporary electromagnetic bonds as they flow. The pattern of these interactions, combined with the thermal sensations caused by evaporation, is what your brain interprets as the feeling of wetness. Every sensory experience you have of the physical world is an electromagnetic translation. Your senses do not detect matter directly. They detect the electromagnetic consequences of electron cloud interactions and convert those into nerve signals, which are themselves electromagnetic, and send those signals to your brain, which processes them through more electromagnetic interactions between neurons. The entire chain from external reality to conscious experience is electromagnetic from beginning to end. There is no point at which physical contact in the classical sense enters the process. This raises a profound question about the relationship between perception and reality. The world you experience, the solid, textured warm or cool, smooth or rough world that seems so concrete and immediate, is a construction. A model built by your brain from electromagnetic data. The actual reality at the quantum level is fields and probability distributions and virtual photon exchanges. Your brain translates this quantum reality into an experience that makes intuitive sense for an organism that needs to survive and navigate at human scales. This does not mean your experience is false. The electromagnetic forces are real. The patterns they create are real. The distinctions between smooth and rough, warm and cold, hard and soft, these are genuine physical differences in how electron clouds are arranged and how they interact with your sensory apparatus. Your brain is not making things up. It is interpreting real data, but it is interpreting that data through a framework, the framework of physical contact and solid objects, that does not accurately reflect what is happening at the fundamental level. You might ask whether this matters. If the experience is reliable, if the world behaves consistently, if tables always support your hands and floors always support your feet, does it matter that the underlying mechanism is electromagnetic rather than contact-based? For practical purposes, probably not. You do not need to think about virtual photons to sit in a chair, but for understanding the nature of reality, it matters enormously, because it reveals that the world is far more extraordinary than it appears. The apparently simple experience of pressing your hand against a table is, when examined closely, an astronomically complex quantum event involving billions of trillions of electrons interacting through the electromagnetic field, mediated by virtual photon exchange, constrained by the Pauli exclusion principle, and interpreted by a brain that is itself a network of electromagnetic interactions. Let us zoom out now and think about the biggest picture of all. You are made of atoms, roughly 7 billion of them. Each atom is a nucleus surrounded by electron probability clouds. Those electrons are excitations of the electron field, a quantum field that fills all of space. The nuclei are made of protons and neutrons, which are themselves made of quarks, excitations of quark fields held together by gluons, excitations of the gluon field governed by the strong nuclear force. You are not made of stuff in the way you probably imagine. You are made of vibrating quantum fields, patterns of excitation in fields that pervade the entire universe. The atoms in your body were created billions of years ago. The hydrogen atoms in your body, the ones that make up roughly 10% of your body's mass, mostly as part of water molecules, are among the oldest atoms in existence. Their nuclei, lone protons, formed within the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. But the universe was still far too hot for electrons to bind to those protons. It took roughly 380,000 years for the cosmos to cool enough for protons and electrons to combine into stable, neutral hydrogen atoms, an era physicists call recombination. Those atoms have existed ever since, for nearly the entire 13.8 billion year history of the universe. The heavier atoms in your body were forged in the cores of stars. The carbon in your muscles, the nitrogen in your DNA, the oxygen in your blood, the calcium in your bones, the iron in your hemoglobin, all of these were created by nuclear fusion deep inside massive stars that lived and died billions of years before the Earth existed. When those stars exhausted their fuel and exploded as supernovae, they scattered these heavy atoms across space. Over millions of years, gravity gathered some of those scattered atoms into a cloud that collapsed and formed our solar system. The heavier elements settled into a rocky planet that we call Earth. And eventually, through billions of years of chemical evolution and biological evolution, some of those atoms arranged themselves into you. But through all of this, through the Big Bang and stellar nucleosynthesis and supernovae and planetary formation and the origin of life and billions of years of evolution, at no point did any of those atoms ever physically contact any other atom. Every interaction along the way was mediated by quantum fields. Gravity pulled the gas clouds together through the gravitational field. Electromagnetic forces shaped atoms into molecules through the electromagnetic field. The strong nuclear force built atomic nuclei through the gluon field. The Pauli exclusion principle gave atoms their size and structure. Every step in the chain that led to your existence was a field interaction, not a collision, not a contact event, a field interaction. You are the product of 13.8 billion years of field interactions. Every atom in your body arrived at its current position through an unbroken chain of quantum field events, stretching back to the origin of the universe. And you are held together right now, in this moment, by those same fields. The electromagnetic bonds between your molecules, the quantum exclusion effects that give your bones their rigidity, the electromagnetic nerve impulses that carry your thoughts, all of it is field interaction. All of it is quantum. And here is perhaps the most remarkable thing of all. You are aware of this. You are a collection of quantum field excitations that has become complex enough to be conscious, complex enough to wonder about its own nature, complex enough to ask what an electron is and to understand the answer, complex enough to realize that it has never touched anything and to appreciate how extraordinary that truth is. Consciousness remains one of the deepest unsolved problems in science. We do not fully understand how the electromagnetic interactions between neurons in your brain give rise to subjective experience. How the firing of billions of neurons, each one a cell communicating with others through electromagnetic signals, somehow produces the experience of seeing red, feeling warmth, hearing music, or contemplating your own existence. This is what philosophers call the hard problem of consciousness, and it remains genuinely hard. But we do know this. Whatever consciousness is, it arises from matter, from atoms, from electrons and quarks and gluons, from quantum field excitations interacting through forces that never involve physical contact. Your thoughts are electromagnetic events. Your memories are stored in the strengths of the electromagnetic connections between neurons. Your emotions are patterns of electromagnetic activity in specific brain regions. Everything you have ever felt, everything you have ever thought, everything you are as a conscious being is a consequence of quantum fields interacting according to the laws of physics. The universe did not have to produce consciousness. There is no known law of physics that requires matter to become aware. Quantum fields could exist and interact and form atoms and stars and planets without anyone ever knowing about it. But on at least one planet, orbiting one ordinary star in one ordinary galaxy, quantum fields arrange themselves into patterns complex enough to look back at the universe and understand something about how it works. Patterns complex enough to discover that electrons are field excitations, that atoms are mostly empty space, that nothing ever touches anything, and that all of this is beautiful. There is a tendency when confronting these truths to feel diminished, to feel that if the world is not what it appears, if solidity is an illusion and contact is a fiction, then somehow the world is less real, less meaningful, less worth caring about. But I think the opposite is true. The world is more remarkable than the naive picture of solid objects bumping into each other. The reality of interacting quantum fields is richer, stranger, more intricate, and more beautiful than any picture of mechanical contact could be. When you feel the warmth of sunlight on your face, what is happening is that photons, excitations of the electromagnetic field, have traveled 150 million kilometers from the sun, crossed the vacuum of space at 300,000 kilometers per second, entered Earth's atmosphere, and been absorbed by the electron clouds of molecules in your skin. The energy of those photons excites the electrons into higher energy states. That energy is then transferred to the surrounding molecules as thermal vibration. Your nerve endings detect the temperature increase and send electromagnetic signals to your brain, which interprets them as warmth. The entire experience, from the surface of the sun to the conscious sensation of warmth on your cheek, is a chain of quantum field interactions. Not one moment of physical contact occurs along the way. And yet, the experience is vivid. It is real. It is one of the most pleasant sensations a human being can have. When you listen to music, what is happening is that pressure waves in the air, created by the vibrating surfaces of instruments or speakers, enter your ear canal and cause your eardrum to vibrate. The vibrations are transmitted through tiny bones to the cochlea, where they create waves in fluid that bend tiny hair cells. The bending of these cells opens ion channels, allowing charged particles to flow, creating electromagnetic signals that travel along the auditory nerve to your brain. At every stage, the interactions are electromagnetic. The air molecules never make contact with your eardrum in the classical sense. The tiny bones interact through electron cloud forces. The hair cells respond to electromagnetic disturbances. And the result is the experience of music. Melody, harmony, rhythm, emotion, all of it created by quantum field interactions. All of it without a single moment of physical contact. The electron is among the simplest entities in the universe, a single excitation of a single field. No known internal structure, no confirmed physical size, just 3 numbers: charge, mass, and spin. And yet from this simplicity, everything emerges. Every element in the periodic table is defined by how electrons fill orbitals around nuclei. Every chemical bond is a rearrangement of electron clouds. Every material, from diamond to water to living tissue, owes its properties to the behavior of electrons. Every color you see is a consequence of electrons absorbing and emitting photons at specific energies. Every electrical device you use works by controlling the flow of electrons through materials. Every thought you think is an electromagnetic event in a brain built from atoms whose properties are determined by electrons. From one simple field excitation, all the complexity of the physical world emerges, and none of it requires anything to touch anything else. The universe operates entirely through field interactions, through the electromagnetic force and the Pauli exclusion principle, and the other fundamental forces described by quantum field theory. And it produces a world that is rich and textured and warm and beautiful and full of things that feel solid and real and touchable, even though nothing is solid in the way we imagine, and nothing has ever been truly touched. You are a temporary arrangement of quantum field excitations. The atoms that make up your body have been around for billions of years and will continue to exist for billions more after the arrangement that is you has dissipated. The electron field excitations that right now constitute the electrons in your brain, carrying the signals that allow you to understand these words, are the same type of excitation that exists in every atom, in every star, in every galaxy in the observable universe. You are made of the same quantum fabric as everything else, connected to everything else not by contact but by the shared fields that permeate all of space. The next time you reach out and pick up an object, take a moment to consider what is really happening. Your electron clouds are interacting with the object's electron clouds through the electromagnetic field. Virtual photons are mediating the force. The Pauli exclusion principle is preventing the electrons from collapsing into shared states. And the collective result of billions of trillions of these quantum interactions is the simple, familiar, unremarkable sensation of holding something in your hand. You have never touched it. You never will. But the interaction is real. The force is real. The experience is real. And it is far more remarkable than physical contact could ever be. Because what is actually happening is the universe doing quantum physics at the most fundamental level, producing a classical world that feels solid and tangible and real, and doing all of it without anything ever making physical contact with anything else. The electron is a ripple in a field. It has no size, it has no surface, and it is the reason everything in your life feels the way it does. The firmness of the ground beneath your feet, the texture of fabric against your skin, the resistance of a door handle in your grip, the warmth of another person's hand in yours. All of it is the electron. All of it is electromagnetic. All of it is quantum. And none of it involves anything touching anything. You have spent your entire life surrounded by this truth without knowing it. Every object you have held, every surface you have walked on, every person you have embraced, every meal you have tasted, because even taste is electromagnetic. Molecules interacting with receptor proteins through electron cloud interactions on your tongue. All of it has been quantum field interactions masquerading as physical contact. The most convincing illusion in the universe, maintained flawlessly for every moment of your existence. And now, you know. You know what an electron really is. You know how atoms are really structured. You know why matter feels solid even though it is overwhelmingly empty space. You know that the Pauli exclusion principle and the electromagnetic force conspire to create the sensation of contact where no contact exists. And you know that this is not a diminishment of reality, but an enrichment of it. The world is not less than you thought. It is more. Incomparably, beautifully more. So when you go about your day tomorrow, when you pour your morning coffee and wrap your hands around the warm cup and feel the heat seeping through the ceramic into your palms, remember what is really happening. Remember that the warmth is electromagnetic radiation from vibrating atoms passing through electron cloud interactions into the electron clouds of your skin. Remember that the solidity of the cup is the Pauli exclusion principle, refusing to let your electrons share quantum states with the cup's electrons. Remember that the smoothness of the ceramic is the regularity of its crystalline surface, creating uniform electromagnetic interactions with your fingertips. And remember that all of this, every part of this simple, everyday moment, is the universe expressing itself through quantum fields. The same fields that fill all of space. The same fields that govern the behavior of matter in distant galaxies. The same fields that have been operating since the first moments after the Big Bang. You are part of this, not separate from it, not observing it from outside, part of it, made of it. A conscious expression of quantum fields, aware of themselves for the first time in 13.8 billion years. And the fact that you can hold a warm cup of coffee and simultaneously understand the quantum field interactions that create the sensation of holding a warm cup of coffee is one of the most extraordinary things that has ever happened in the history of the universe. Nothing touches, but everything connects. Through fields, through forces, through the elegant quantum rules that govern all of reality. You are connected to the cup in your hand, and to the chair beneath you, and to the ground beneath that, and to the earth, and to the sun, and to every atom in the observable universe by the same quantum fields that create the illusion of contact and the reality of interaction, not connected by touch, connected by something deeper, the shared quantum fabric of existence itself. Thank you for joining me on this journey into the heart of what matter really is. If you found this exploration valuable, a like or subscribe would mean a great deal. It helps me keep making these deep explorations of how the universe truly works. And remember, you have never touched anything. Not once, not ever. But what has actually been happening every time you thought you were touching something is far more beautiful, far more intricate, and far more wonderful than simple contact could ever be. You have been interacting with the universe at the deepest possible level, field to field, quantum state to quantum state, electron cloud to electron cloud, connected not by contact, but by the invisible, magnificent forces that hold all of reality together. Good night, and may you never think about touching the same way again.